All right, so let's do an example here involving the Carnot cycle. We have a Carnot heat engine. Air is the working fluid. That's what's inside the piston cylinder device. So let's put up our schematic. So we have air in our piston cylinder device. So air, if we apply any kind of conservation relationships like the energy balance, the air inside the piston cylinder device is going to be our system. Okay? So you have a Carnot cycle, air is the working fluid or the system. The heat transfer to the low temperature reservoir during the cycle is 3.4 kilojoules. The high and low temperature reservoir temperatures are 300 and 250 degrees Kelvin. This is going to be a constant specific heat problem. I'm going to find a quantity called K. K, which is the ratio of the specific heat at constant pressure, Cp, divided by the specific heat at constant volume, Cv, and I'm going to set that equal to 1.4. I'm going to assume constant specific heats, and I'm going to fix the ratio of Cp to Cv. This will help with calculations. This will make it relatively easy to do calculations, as opposed to using air tables, which can be much harder to do, okay? The amount of air, the working fluid, is 0.1 kilograms. The minimum and maximum volume in the cycle is 0.01 cubic meters and 0.0254 cubic meters. So the min and max volume in the cycle. I think before we get started here doing any work, I'll tell you what we want to do for a second. Let's actually put the cycle up on the TV diagram. I think it's a really good idea to put up the TV diagram so that we understand what's going on from state to state. So temperature, volume. Remember, state 1 is the minimum volume, maximum temperature. 1 to 2 is isothermal heat addition from the high temperature reservoir. That's 1 to 2, isothermal heat addition at TH. And then we have adiabatic insulated, adiabatic expansion from 2 to 3. Then we have isothermal compression at temperature T low, and that results in heat being rejected to the low temperature reservoir, and that goes from 3 to 4. And then we have adiabatic compression back up to state 1, insulated. Okay, so I would definitely, if you do any problems with the Carnot cycle, you need to put up a TV diagram to keep track of what's going on. Now, what are we supposed to find in this problem? We're supposed to find the pressure at state 1. So I want to know the pressure at the top of the cycle here. That's presumably the maximum pressure at that point. Maximum temperature, minimum volume. Presumably the pressure is maximized. Then I want to know what the heat transfer is from the high temperature reservoir. And I want to know what the efficiency is of the cycle. There's actually 2 ways to calculate the efficiency. Oh, I'm sorry here. Let's kill this.